Hello, myself, Jim Alexan Kavala, 21BCE5436. I'm here to present NAN to address Project 3. Computers operate over time and it becomes necessary to address the necessary issues related to time. The first requirement for dealing with time is the ability to reuse hardware to perform multiple computations. Rather than using hardware for a single computation, disregarding it, the goal is to reuse the same hardware for subsequent computations. This is achieved by thinking in terms of the time steps and using loops in software programs to perform repetitive tasks. The important aspect of time is the ability to remember intermediate results. For example, when adding a series of numbers, intermediate results need to be stored to compute the final total. This requires maintaining the state of the computation over time. It is crucial to ensure that computations are not performed faster than the computer's capabilities or to have an understanding of the computer's speed. To handle time in computer systems, a discrete time model is adopted. This involves using a clock which acts as an oscillator with a fixed rate. Each cycle of the clock represents one discrete time unit. By breaking down continuous physical time into these discrete time units, the complexity of dealing with continuous time is simplified. Within each time unit, nothing changes and computations are treated as instantaneous. Physical signals and electrical implementations of circuits do not change instantaneously between time units. There are delays involved in transitioning between different logical states. However, by choosing an appropriate clock cycle that allows enough time for stabilization, these delays can be disregarded and the system can be treated as if it operates instantaneously within each time unit. Sequential logic is a concept where the output at a given time depends on the input at the previous time step. This allows for the retention of information from the past and the ability to build on previous results. It is emphasized that combinatorial logic deals with instantaneous computations within a time unit, while sequential logic incorporates information from the previous time step. By adopting a sequential logic approach, it becomes possible to have the input and output values live in the same wires or best lines. This allows for the concept of state where the value at a given time depends on the previous value, enabling the system to change state and build on the previous results. There is a need for elements in computing systems that can handle time and logical sequential logic. It emphasizes the importance of having an element that can remember one bit of information and move it from one time unit to another. This element is called a flip flop, which can flip between two physical states and remember the information between time units. The main focus is on the specific type of flip flop called the clock data flip flop, which has a single input and output. It remembers the input from the previous time unit and outputs it in the next time unit. The functionality of the clock data flip flop is explained using a diagram that illustrates how the output corresponds to the input at the previous time unit. Bit chip is a chip that can remember a bit for hour. It is defined by two inputs, an input bit and a load bit. When the load bit is set to 1, the chip remembers the input bit. When the load bit is 0, it keeps remembering the last loaded value. The input and the load signals are provided and the output of the bit chip is determined based on the input and previous output values. The implementation of the bit chip using a flip-flop and multiplexer is described step by step, showing how the output is determined based on the input and load signals. Bitchip is a primitive block that can be used to build other sequential logical elements such as memories and counters. Memory is classified into three types, such as main memory, RAM, and secondary memory, hard disk memory sticks. There is also a distinction between volatile memory, example RAM, and non-volatile memory, example disks, based on whether the data is retained when the power is disconnected. The RAM unit is composed of a sequence of addressable registers where each register stores a 16-bit value. The registers can be read by prompting the output, which reflects the current state of the register. To write a new value, the input is set to the desired value and the load bit is asserted. This causes the register to store the new value and starts emitting the updated value from the next cycle onward. The address input determines which register is selected, and the output reflects the state of the selected register. Reading from the RAM device involves setting the desired address and prompting the output. Writing to the RAM device requires setting the address, inputting the new value, and asserting the load bit. Now, let me talk about family of RAM. Family of RAM chips vary with sizes. RAM 8, RAM 64, RAM 512, RAM 4K, and RAM 16K. These chips are necessary for building the hack computer platform. Counter chip. The counter chip is designed to facilitate the execution of a program consisting of instructions for the machine. The counter chip needs to support three basic operations: fetching the first instruction, fetching the next instruction, and going to a specific instruction. These operations are accomplished through the use of control bits, load, increment, and reset. The reset functionality of the counter chip is as follows: if the reset bit is asserted, the counter emits 0, effectively resetting it to its initial state. The load bit is asserted, the counter is set to a specific value indicated by the input. If the increment bit is asserted, the counter increments its current state by 1. If none of the control bits are asserted, the counter emits its current state. The control chip consists of a 16-bit input and a 16-bit output, and three control bits. The counter chip's behavior is determined by the state of these control bits. Now let us talk about the project 3. Project 3 involves building chips that implement memory functionality. Project 3 focuses on constructing memory related chips starting from base registers to more complex RAM devices and a program counter. The projects begin with the previously designed chips from projects 1 and 2, including a primitive data flip flop. The task is to construct various chips starting with a 1-bit register followed by 16-bit register. Next, the focus shifts to building RAM, random access memory devices. The RAM can be constructed by grouping smaller RAM parts, stacking 8 1-bit registers, create a RAM 64 chip. Similarly, 8 RAM 64 chips are combined to form a RAM 512 chip, and this process continues until a RAM 16K chip is achieved. Now, I will show you the how we can simulate the hardware simulation of some of the chips that we have implemented using in this project 3. I will show you how we can the hardware simulation of the bit 1 register that they have implemented. First, we have to load the chip that we have implemented. We have to load the chip file. Then we have to run the test script file, and we have to run it. The output gets logged over here in this output terminal. Now I will show you the hardware simulation for the RAM, uh, the PC. We have loaded the PC with the hardware simulation language and the input pins and the output pins as well as a dummy value. Then we are gonna run the test script file. After running the test script file, the output is loaded over here. Now I will show you the hardware simulation for the RAM 8 HTL chip. We have to load the test script as well. Similarly, we can execute all these registers using the hardware simulation tool, and we can include this memory functionality in the hack computer that we are going to implement. Thank you, Abdul Qadir, sir, for giving me this opportunity to present the DA3. Thank you.